Guys, let's look at this very example. That's example number 1 under non-exact differential equation. So we have solution. Of course, the equation is in the form of m dx plus n dy as usual, so that m is equal to x squared plus y squared plus x, and n is equal to xy, m is equal to xy. Just comparing this equation with this given equation, then we can be able to figure out this. So now, the partial differentiation of m with respect to y, to check whether the equation is actually exact or not. With respect to y, this is constant x0, it's constant x0, then differentiating only this will give us 2y. And of course, partial differentiation of n with respect to x here, differentiating x is 1 times y is actually y. Alright, so it is evident that partial differentiation of m here with respect to y is not equal to the partial differentiation of n with respect to x. It's not exact. So now we are going to find the integrating factor. We're going to find the integrating factor. Alright. And to find the integrating factor, mu, we check if the partial differentiation of m with respect to y minus partial differentiation of n with respect to x all over n, we check if it is a function of x alone. And we can examine that. Since the partial differentiation of m with respect to y here is 2y minus the partial differentiation of n with respect to x here is y all over n, and of course n is xy. And that's equal to, let's check if it's a function of x actually. So 2y minus y is actually y over xy, and then y cancels y there. We have 1 over x. As you can see, the function of x is out. So actually, the partial differentiation of m with respect to y minus that of n with respect to x all over n, when evaluated, is a function of x alone. Therefore, we can use this to find our integrating factor. If not, we can take the alternative. So now, our integrating factor mu is exponential integral of f of x dx. So in this case, we have our integrating factor mu to be equal to exponential integral of f of x is 1 over x dx. Is that okay? So this is equal to exponential, the integral of 1 over x is ln x, right? Then which is actually equal to this ln is the same thing as log to base e. So we have exponential logarithm to the base of e all multiplied by x, where logarithm to the base of e is the same thing as ln. Then when the two base, this is the base, and then the logarithm is having the same base, of which the standard base, that's the major base, is the same as the base of the logarithm. And when this happens, the answer is equal to what? X. That is one of the laws of indices. One of the laws of logarithm, sorry. So when we have a major base having the logarithm to be of the same base here, definitely the answer becomes x inside. Alright, so our integrating factor now is equal to x. So we are going to multiply the given equation by our integrating factor mu. To multiply the given equation by the integrating factor mu so that we check if the equation is now exact or not. Alright. So multiplying this equation with mu, we have the integrating factor mu multiply this guy here, multiply this guy with mu, and also we multiply the xy mu times xy dy equal to 0. So multiplying both sides with the integrating factor, and of course the integrating factor mu is equal to x. So that here becomes x by x squared plus y squared plus x dx plus x dot xy dy equal to 0. Okay, x multiplied by x squared is x cubed, x to that is x y squared, x multiplied by x is x squared, all the x multiplied by x is x squared y dy equal to 0. So we have a new equation here, of which we are to check if the equation is now exact, having multiplied by the integrating factor. Okay. In this case, m similarly is equal to x cubed plus xy squared plus x squared, and n is equal to x squared y. So partial differentiation of m with respect to y here, as usual. This is constant, so both is 0, both are 0. So differentiating this guy with respect to y will give us 2 coming down will be 2xy. And of course, differentiating this n with respect to x partial, 2 coming down here will give us 2, remove 1 from the power, we have x, y. Wow, as you can see, the partial differentiation of n with respect to y is now equal to the partial differentiation of n with respect to x. The equation is now x. So here, partial differentiation of m now with respect to x is now equal to the partial differentiation of n with respect to x is now x. So we can now go ahead to solve the equation. Okay, having confirmed the exacts, we can now say there exists a function z of x, y such that partial differentiation of z with respect to x is equal to m. Alright, so integrating both sides, we have integral of both sides with respect to x. Integrating this will give us the function z, that's integrating the z will give us z. Then integral of m with respect to x goes by constant c of y. Because we keep y constant, y integrating, therefore the constant here should be a constant which is a function of y, since the integration is with respect to x and y is considered to be the constant, so the integral should be a constant. So we have z is equal to integral. Of course, what is our m? M here is equal to x cubed plus xy squared plus x squared with respect to x plus c of y. Okay? So integrating this with respect to x, we have z equal to, with respect to x, will give us x raised to the power 4 over 4. With respect to x here is x raised to the power 2y squared. We add 1 to the power, bring the power down, which is 2. then incrementing x here is x raised to the power 3 over 3 plus c of y. Alright? So this is our main original equation. This is our main equation, and of which we are going to find the value of c of y to have a complete solution. So for us to find the value of c of y now, we are going to differentiate this function with respect to y. So there exists also the second instance, which is partial differentiation of z with respect to y now equal to n. Right? So the first is partial differentiation of z with respect to x is n. The second is partial differentiation of z with respect to y is n. Meanwhile, what we are now differentiating here is this particular function here, so that I have the partial differentiation with respect to y of the value of z there is x raised to the power 4 over 4 plus x raised to the power 2y squared over 2 plus x raised to the power 3 over 3 plus c of y equal to n. And of course, n is equal to x squared y, so equal to x squared y. Okay? So we're going to differentiate this function now with respect to y alone. Okay. Alright, with respect to y alone, this guy doesn't contain y, is a constant. To close it down. Then with respect to y, by differentiation, we bring 2 here. We're going to have 2x square y, remove 1 from the power of y, all divided by 2, plus differentiating this guy with respect to x, with respect to y, we close it down because it doesn't contain y. Then we get to this guy now. Differentiating c of y will give us c prime of y equal to n, which is x squared y. Coming here, 2 can cancel 2, so that we have x squared y plus c prime of y is equal to x squared y. So x squared y can cancel from both sides. We have 0 here, so that c prime of y is equal to 0. Then to get the value of c of y, we integrate both sides, so that we have c of y is equal to k, because the integral of 0 is equal to k, which is a constant. So now, since we know the value of c of y, we can substitute it in this main equation so that we have our final answer. Therefore, z is equal to x raised to the power 4 over 4 plus x raised to the power 2 y squared over 2 plus x raised to the power 3 over 3 plus c of y, and c of y is equal to k. You can take k to this side, so we have z minus k is equal to x raised to the power 4 over 4 plus x squared y squared over 2 plus k. Taking k to that side, okay, plus x raised to the power 3 over 3. Then where z minus k is equal to a, to have a complete solution, we have a is equal to x raised to the power 4 over 4 plus x squared over x squared y squared over 2 plus x cubed over 3, where a is equal to z minus k. And eventually this becomes the solution to the non-exact differential equation. Thank you and God bless you.